Hello! So in this video, we're actually going to be doing two types of convergence of functions. So in the book we're using, at least at the time I'm recording this, these are actually done in separate sections, but I'm choosing to combine them because one of them sort of motivates the other, and it's really helpful to see them in juxtaposition, right? See them side by side so you can see what the key differences are, okay? So we're going to start with pointwise convergence of functions. Now, pointwise convergence is basically the kind of convergence that you have been sort of taught and encountered this whole time. So when you have sort of in the past shown that some sequence converges, you're doing a sort of version, in some sense, of pointwise convergence. So here, I'll just give the definition. So Fn, this is a sequence of functions, right? So let Fn be a sequence of functions. And we say that Fn converges pointwise to some function g if we have the following. For every epsilon greater than 0 and any x real number, there exists this capital N. This isn't usually included in the definition. I'm doing it to really drive home. This capital N depends on x. Right, so you're given the x before you choose the n, and this is a key difference between the two, so that's why I'm drawing attention here. So there exists a capital Nx such that if little n is bigger than this nx, then Fn of x minus g of x is less than epsilon. So essentially, given a point, given an epsilon, you can choose some deep enough part of the sequence of functions such that any function after that point in the sequence is within epsilon of your target. So we call g this pointwise limit of functions, this pointwise limit of Fn. And often we will write this as Fn of x converges to, right, the right arrow, g of x. Okay. So as I mentioned, this is sort of the one that this is the function context of the type of convergence you've already learned. And a perfectly valid question would be, why do we need a different type, right? Why would we need to learn more than one type of convergence? This has been working well so far. And the answer is because, as it turns out, when we move to functions, right? So before we were doing sequences of numbers, which are sort of, you can think of them as constant or constant functions. Now we're doing sequences of actual functions that aren't constant anymore. And when we make that jump, it turns out that this pointwise convergence is really frail. It's a very weak type of convergence. Because really what you would like in a perfect world is that when you have some sequence of functions and all those functions that form the sequence have some property, like they're all polynomials, you would like that the result that it converges to, the g, also has that property, like g is also a polynomial. Turns out that's not true. And in fact, with pointwise convergence, it's really easy to break that. So for example, let's look at Fn of x being the most basic monomial we can, x to the n, right? So remember, this is a sequence of functions. So f1 of x is x, f2 of x is x squared, f3 of x is x cubed, etc. Right? And so our sequence looks like x squared, x cubed, x to the fourth, x to the fifth, dot, dot, dot. Now the question is, what is the pointwise limit as n goes to infinity of Fn? So let's see what happens. Well, to do a pointwise limit, the idea here is that you fix the x before you take the limit, before you do the limiting process. So what this tells me then is that I can look at this by fixing some x value and see what happens as n goes to infinity. So for example, if I fix, say, 0, right? Like, let's say these fn's, because I didn't actually give you a thing, let's say these fn's are from 0, 1 to r, just to make life easy for us for a second. So when x is 0, 0 to any power, if it's honestly 0, that's going to be 0. If I get something small, like 1/2, then every time I take a power of it, it gets smaller, it goes closer to 0. So if I take infinitely many powers, I'm going to get something infinitely close to 0. And in fact, if I take anything between 0 and 1, not including 1, I keep getting 0. So really what this ends up being is 0 for when x is 0 up to but not including 1. But once I get 1, well, 1 to any power, if it's honestly 1, not just close to 1 or approaching 1, honestly 1 to any power is still 1. So in this case, my pointwise limit is this weird thing that looks like, right, it has, I start off with sort of a, let me do this in different colors so that it might be easier to see. I start off with x, then I get x squared, then I get x cubed, then I get x to the 4th, then I get x to the 5th. And so my end result, after I've done this enough times, if I take my limit, is this thing that looks like just the 0 function all the way up to 1, and then 1. So I took what is arguably one of the nicest functions we could have, x to the n, a monomial, no coefficient, just x to the n. And when I took this pointwise limit, not only did I not get a polynomial, I didn't even get something that was continuous, right? It jumps. So I've broken this very badly, right? And wait, because it's even worse than that. Because what happens if I take this fn, the same fn that I've described, and I look at the limit as x goes to 1 of the limit as n goes to infinity of fn of x versus doing the same thing, but I'm going to do the limits in the other order. N going to infinity of the limit as x goes to 1 of f of x, fn of x. Okay, so if this thing is g, right, so I'm going to say this is g of x, which equals that. Then here, my limit as n goes to infinity of fn of x is g of x. So this equals the limit as x goes to 1 of g of x. But remember your section from limits, even in calculus, right? I don't care what it is at 1, I just care what it's doing as it approaches 1. And here it's 0, all the way up beforehand. So this is literally 0, right? But on the other hand here, well, each of the fn of x's, these things are continuous functions. So their value is just whatever it is when I plug in 1. But for x to the n, for any n, I get 1. So this is the limit as n goes to infinity of the function 1, which is obviously just 1. That looks like a 7. There we go, 1. So not only did using a pointwise limit, I don't know why I can't talk, not only did that spectacularly break such a nice polynomial as x to the n, but somehow even worse is that taking the exact same expression but switching the order of the limits gets me drastically different answers. So this tells me that if I try to do a pointwise limit, I can't switch the order of the limits. It can make a difference, right? I can't just do whichever limit is the easier one and then do the other limit. Can't do that with pointwise limits, okay? Spoiler alert, that's why we have uniform convergence, but we'll get there. Last but not least, I just want to point out, because this is one of those that's really sort of unintuitive initially, which is if we have instead, let's look at, I don't want to take up too much room here. Let's look at fn of x is x over n. For here, fn going from r to r. The pointwise limit, fn of x, converges to g of x, which is honestly the 0 function. And this is because The whole point here, the key idea for pointwise limits is that you fix the x, then you're taking a limit. So for whatever x I pick, 17, as n goes to infinity, 17 over n goes to 0. So even though I can pick x as arbitrarily large, this is still pointwise the limit 0. Okay? So don't be confused by the idea that, like, because I have some finite number here, that's why I get 0. I mean, in this case, that's sort of right between 0 and 1 is necessary for the power, but the point being that I can have x be arbitrarily large, but it's fixed before I take the limit with the n. Okay? So x can be arbitrarily large, but then n will eventually be bigger, even if x could always be chosen bigger for a fixed n. That's not the order it works. Okay? All right, so that's the pointwise one. But the motivation here is that we would like some idea of convergence that doesn't lose these features we like, right? We like that a polynomial stays a polynomial, or at the very least, we would want something that is continuous to stay continuous. Maybe we can't get that it's a polynomial, but we should at least keep something as fundamentally important as continuity, right? And on top of that, this whole like switching limit order thing is a disaster waiting to happen, because there's plenty of times where limits are easy to do in one way and hard to do another way. So an example of that would be like if you're trying to integrate fn, right? If you want to take the limit of the integral of fn versus the integral of the limit of fn, right? Doing it one way versus the other, one of those is almost always vastly easier. So this is where we get the uniform convergence. So uniform convergence of functions. So again, we have these fn's, the sequence of functions. We say that it converges, the fn converges uniformly to some function g if we have the following. So we have for every epsilon greater than 0, but notice here it gets right to there exists some n, so I'm not talking about x yet, such that if n is bigger than capital N, note that capital N not depending on x, then fn of x minus g of x is less than epsilon for all x. Okay, so we call g in that case the uniform limit of fn, and here we write fn converges to g as opposed to fn of x converges to g of x. So the author at one point in the book claims that it doesn't matter how you write these things, and I would argue that that is misleading in most texts, because this is a very standard convention. Of x usually implies a pointwise limit, versus without the x implies some sort of uniform limit. So the whole fundamental difference between these two things, and this one sort of does a lot more for us, so it's a big difference, but the fundamental difference is that here I get to fix the x before I figure out capital N, here I do not, okay? So for example, let's claim, so let's have fn of x equal x over n for fn going from, let's say, 0, 1 to r. So we claim that fn converges to g, where g is the 0 function. So in particular, I'm claiming here that this is a uniform convergence, okay? So over here, if I did this, I'd say, okay, epsilon greater than 0 be given, fix some x, then I'd find capital N and move along. Here, I'm going to start with let epsilon greater than 0 be given. Choose n such that 1 over n less than epsilon. Then, so notice here I don't have anything about x, just 1 over n less than epsilon. So f of x minus g of x. So I'm just going to start out with what is that? Well, that is, fn of x. So this is x over n, that's what fn of x is, minus, and I'm claiming g is 0. So this is just x over n. But x over n, x is between 0 and 1. So in particular, whatever x is, and again, I haven't fixed it or said anything about it, but I know this is going to be less than or equal to the biggest x can be, which is 1 over n. Right? But if I've chosen now, right, if I'm using n bigger than capital N, then replacing the bottom with a smaller thing, which I guess I should have strict there, although I can leave it as equals. This is going to be 1 over capital N, which I can take off the absolute value because I know that's positive, but I've chosen 1 over capital N to be less than epsilon. So I've got my fn of x minus g of x is less than epsilon, and I never needed to fix x or do anything with x. That was just a direct consequence because I could do some sort of information with x. Even though I had no idea of what x was, I knew it was less than 1, and that was the key. Okay? All right, so we're going to be doing a bunch of stuff with uniform convergence, so we'll have more examples coming up. But the real takeaway here is that with uniform convergence versus pointwise convergence, uniform convergence gives you vastly more idea of what you're getting out the other end, what the properties of G are, right, when you get some G that it converges to. Whereas with pointwise, terrible stuff can happen. The downside is to prove something converges uniformly, here you have no control over x when you have to pick n. So you have to pick n that somehow magically works for every x no matter what. And that can be tricky. Over here, you could fix x and then choose an n that's based on x. It's much easier to prove. Okay? All right. So with that, these are the different types of convergence. And we are done.